Alright, what's going on, guys? So today we're going to be talking about the path integral formulation for quantum field theory. So in this video, we are going to set up the problem. We're going to set up path integrals. We're going to see exactly what they look like, and we're going to sort of dissect them in detail. And then we're going to go from there. So without me talking too much, let's get right into the material. But before I do that, make sure to hit that like and subscribe button. And let's get on with the content. So today we are talking about the path integral formulation for quantum mechanics. What I have here, before we actually go into the topic here, as you know, I've started to, I'm going to start ramping up production of many of these videos. We're going to be, in the next series, you guys have spoken, I'm going to be talking about the symmetries of physics. We're going to go deep dive into particle physics within that sort of front, right? We'll be talking about the SO, the special unitary groups, the orthogonal groups, and all that kind of stuff, and how invariant quantities of, say, the Lagrangian play a role in those types of symmetries, right? But anyways, I digress. Let's get back into the path integral formulation for quantum mechanics, or quantum field theory. So the path integral formulation, we're going to start off with a very simple picture here. So the picture is, we have this we have this graph, right? So the graph, we start off with some initial state, right? This is Q, right? So Q, if you remember from way back then, we had Q representing some state, and the canonical momentum associated with Q is, we'll call this canonical momentum, so C momentum. So this is just notation to keep in mind. So we have the sort of the state, right? So the state sort of the position, right? So you need position and momentum to describe the overall state of a particle. So this is probably not the best wordage. So I would say position. Again, in phase space, right? So in phase space, we're talking about Q's and P's, and we're talking about this is sort of the background that the Lagrangians are placed on, right? So we have the states, which are described again by the location of particles and their momentum, right? So then those two variables constitute a phase space, and Lagrangians in that phase space correspond to a path in that space. So this is just a little bit of a reminder as to what these things are. But let's get, so when we talk about this picture here, so we have sort of the phase space encapsulated in this axis, and then we have time in the other axis here. So we have time right here. And what we want to do is we want to basically construct a path, right? So paths in phase space, we talked about, were Lagrangians. Lagrangians were functions of Q and Q dot. If you remember from way back when, this Q here and Q dot, right? So Q dot, again, was the canonical momentum. And we talked about Lagrangians in that context. They were paths in phase space. When we talk about adding this dimension of time, now we go from talking about Lagrangians to talking about actions, and we're going to see how actions play a role here. But let's draw, when we draw this out, we're drawing a path, right? From a state at an initial time 0 to state at an initial time, at a final time t. And we draw these lines with an intermediate state of Q1. Okay, and we draw, so the first line is the path taking us from state A to Q1. And then this line here represents the path taken from state Q1 to state B. And this is how we're going to denote this, right? So from A, we use the Hamiltonian to push A into Q1. That's how I kind of like to think about this. So A goes to Q1 by means of an exponential of the Hamiltonian. And then we go from Q1 to state B by means of an exponential of the Hamiltonian again, with t being the final time minus t1, right? Because we want this difference, not this difference. Not supposedly, but ideally we are making this difference here the same as the difference between t1 and 0. Okay, so let's complicate things now. So now suppose we have multiple paths. Suppose a particle can go from state A to state B in multiple different ways. So how do we represent that? Well, we represent that through multiple different paths, and there's a Q1 for each path, right? So when we mathematically enforce this guy, this picture right here, this picture that we have up here, we have, okay, we're going from state A by means of the Hamiltonian to Q1, and then we go from Q1 by means of the Hamiltonian again to state B. And then we go from B, and then we sum over Q1, right? So A to Q1, Q1 to B, and we're summing over all the different Q1s, right? So this summation, this is important to keep in mind, this summation here applies to a sort of this downward sum, right? We Q1 here, Q1 here, Q1 here. So whatever number you put right here, right, that's going to specify how many Q1s or how many paths we're looking at. Okay, so, and we're just going to forget about that for right now, because if we want to consider an infinite number of paths, then it's kind of not worth putting a number there. So we're just saying, this is a very general way of saying we are just summing over all possible Q1s. Okay, let's complicate things even more. So now suppose we have multiple stopping points, multiple intermediate states. The way we're going to do this is we have this picture right here, right? So we have a bunch of Q1s, we have a bunch of Q2s, and then we have a bunch of intermediate states between those, and then we have Qn minus 2s, Qn minus 1s, and then B. Right, so the n minus 2 refers to the number, the state number, right? So if we're going through 15 states, say, we're from A to B is a total of 15 states, well, Qn minus 1 is 14, and Qn minus 2 is 13, and so on. So mathematically, what we do is we do the exact same thing, right? We're going from A by means of the Hamiltonian to Q1. And this delta now is the difference between each time interval. So we have this delta right here. Okay. And then we go from Q2 to Qn minus 1, from Qn minus 1 to our final state, which is B. And we're summing over all Q1s to Qn minus 1. So each one of these, every time you look at this guy right here, think of this, you can think of this guy as sort of a downward sum on this picture, right? So we're summing over all Q1s. That's what this means right here. Summing over all Q2s. That's what dQ2 would look like in here. Okay. And we want to calculate, so what we're interested in now is we want to calculate a column, right? So we can think of the column of Q2s and the column of Qn minus 2s and Qn minus 1s. We want to sum down this entire column. And so we basically want to figure out what this guy is, right? Because it's one thing to just state this. The next thing we want to do is try to mathematically determine exactly what form these guys look like. Are they exponentials? Are they log functions? Well, let's take a look. Right, so the way we start this is we say we're going to denote Qj minus 1 and Qj, or Kj plus 1, sorry, like this, right? So we're going from Qj to Qj plus 1, right? So this is this guy right here. Same thing, same exact thing. Qj plus 1 by means of the Hamiltonian. So we now use our Taylor approximation to then we place that in here, and everything stays the same. And then we have, then we can multiply everything out. So this one, so this one here is going to go to this guy, and then this guy here is going to go right there, and then we're going to have higher order terms over here. But we're going to forget the higher order terms for right now, because higher order terms correspond to higher energy terms, and oftentimes those higher energy terms are just inaccessible to us by the current technology that we have. So we're just going to do a second order approximation here, and when we calculate this guy, right, so our Hamiltonian, so we take these constants out, and our Hamiltonian looks like this, right? So this is the sum of our potential and our kinetic energy. Okay, we put a Qj plus 1 in here because we're going to the J plus 1 state, and we go so we go from here to here, right? We have this guy stays the same. This guy, all these guys stay the same. This here, I can zoom in a little bit here. This here is just 1. This is our completeness relationship. If you remember from a while back, we talked about our completeness relationship. And then we go from this guy, or so we go from this to this, right? So we take this guy, we bring it over here, and now we have this. Okay. To go from here to here now, this is not too difficult, right? Because we take a look at this guy, and that's just an exponential, right? So, so the way we see that, right? So this is something we've seen before also, or you can look up other places, but this here is right here. This is equals the exponential of I pj times jq. Okay. And we say the other one is equal to this, q j plus 1 pi with a positive sign. Now here in the way that's a positive sign is because of this relationship right here. When we multiply these two relationships together, we see that we get 1. Okay. And then, so we have this, and now, let's put another bracket there. So now we have this guy right here, right? So we just lump all of these guys into one exponential. So by factoring out PJs, the PJs, and getting these guys right here. Right, so we have our negative sign on our QJ and our positive sign on our QJ plus 1 right here. Okay, and then just coming over to this delta distribution really quick. So this guy, we said exactly the same thing. This should be an E, right? Like that. All right, so we have another page. So for one column, like we said, we get this plus higher order terms with this minus sign, right? So I said plus, but you can think of plus as being subtracting a negative, say. But then we get to get from here to here, now we just plug everything in, right? So we said this guy was equal to all of this, and we said this guy was equal to this. Now we can combine some things, right? So we take this guy and we factor it out because we have it here and here. So we factor it out, right? So we have a 1 taking the place here. Then we have our Hamiltonian out here with their constants plus higher order terms. Okay. Now, what we want to do is we want to take, so we have this guy, and we have this guy. If we notice here, this is an exponential, right? This is 1 plus some, we can compact this into an exponential, right? So this guy here is equal to this guy, right? This is, again, a Taylor approximation of this. And it's not too difficult to see that. if you do multiple, you can do multiple higher order terms to prove to yourself that that's the case. But again, we can write this again as an exponential. So by combining all these guys into a single exponential, now we get this, right? So this delta comes out, and so we need to divide this by delta, and so we get this guy right here, and this is our end result, right? So this, for one column, right? So if we go back to our original picture, for one column here, we get this exponential equation. So I'll just write that column equals that exponential equation, where again we are, when we look at this summation, right, we're summing in this case because we because of the completeness relationship, we had to introduce canonical momentum values, right? So the canonical momentum values again are pj, and so we're summing over all the possible pj's. So we're summing over, we specify how many paths are along this integral, right? So that would be equivalent to saying, well, how many, say, n minus 2's are there, right? In this picture, we only have 3, but you got a 4, 5, 6, or 7. That's what that integral is dealing with. And so plugging this back into our original equation, we get this, right? So I've highlighted a few terms where the j plus 1's are, where the j's are, or right here and right here, and then our n minus 1's, I just also placed in blue for no real apparent reason. This color coding just helps, I think, helps the eye organize things a little bit better. But anyways, by understanding, by coming to this, we came to this before. We understand this now as a we multiply all these k q's, right? So this is some k value, this is some k, this is some k. So we're multiplying them. So that means we have to use this right here. This is instead of a summation sign, this is a multiplicative symbol. And we are multiplying all the QI's. So that's right here. And we're multiplying all the columns together. So now, so we've calculated this guy, right? So we placed that in here. And if we notice, P times the change in Q's, right? So when we go back again here, we're going from here to here. This is a change in Q values. Well, that is Q dot, right? That's the change in Q's. Here's our Hamiltonian. This is something we came to before. So this is really just our Lagrangian, right? So this is what's in our bracket here is really just a Lagrangian. And we can also replace the summation here with an integral in the exponent. And what we get is this right here. If we flesh this out in its entirety, right, so we're summing over QJ's, right? So this is the Lagrangian of all from all the Q1s, right? So there are many values for Q1, and each depicts the position of some particle in state space, right? So, or phase space. And then we have LQ2, LQ3, and so forth. However many LQs, or however many Qs we're specifying again, right? Because again, we go back to this picture. We say, okay, well, we have here's Q1, Q2. We could say there's 20 intermediate steps from going from A to B. That's exactly what we're talking about. So there's a few things here we want to keep track of, right? The one thing we want to keep track of is going across columns in this picture, right? So across columns this way, and then going down columns, we want to take that into account also. Going across columns, this exponential is going to help us. going down the columns again, we're summing over all Q1s, say, and that's what this guy right here helps us with. This, so we have two summations, right? We have this summation and this summation, and we take this guy and we compact it into something called big D little q of t. This is a path integral measure. Right? So this thing is called the path integral measure. And this tells us how many columns we want, right? And so with that all being said, we can compactify this now into the path integral. Now this is just a constant, right? So let's actually not deal with this right now. This is something that can be derived later. It's not derived in the book at all. But what we're actually interested in, this is sort of somewhat of a normalizing constant. What we're actually interested in is this integral right here. So whatever bounds we place on this integral tells us how many paths we want to consider, right? Because again, this integral is an integral over q1 of t, q2 of t. This is one integral, second integral, q3 of t. This is our third integral, and so forth. And so however many q's there are, that's going to tell us that's going to be specified by the bounds on this integral. So if you say you have, again, 20 intermediate states between a and b, then that's what this integral is going to take care of. Whatever bounds we place on the integral, again, tells us how many paths to consider. So if we go back to this picture right here, where that integral, what that integral is doing is it's taking into account q1, q2, q3, 4, 5, 6, 7, 8, and say 9, right? And then when we want to consider summing down a column, well, that's what these guys do, right? And we calculated these guys again. We calculated those guys again to be this right here, more specifically, this right here. So that's the path integral, right? So it's a lot to take in. And the book again that we're going over is not totally keen on going too deep into the path integral. What we are going to do next is we're going to talk about the path integral more on the level of quantum mechanics, right? So what we've done so far is really just more classical than quantum. What we want to do next is go into quantum, take a look at what these actually mean in the quantum realm of things, and hopefully we'll get a better understanding of that, and we'll see how this all plays out in the quantum realm. So again, if you like this kind of content, make sure to hit that like and subscribe button, and I'll see you guys in the next one.